Hello again. Welcome to Chapter 7. We're going to start to use what we know about trig functions to be able to solve equations. Something that might say sine of x plus cosine of x equals some number, or we might learn how to graph it in order to solve it. But first, before we can do anything, we have to figure out how to do algebra with trig functions. So that's what we're going to do today in our 7.1 lesson. This chapter, so I've got up here, learn the basics of manipulating with trig functions, and then use algebra and trig functions to solve for x. So that's the goal for the chapter. Today, we're going to look at 7.1 identities and their uses. And we have talked a little bit about identities, except we haven't defined it specifically, but that's today's lesson. Yesterday, we were supposed to have a card sort, but I didn't have that worked out. It didn't go as well as I thought it would in one class, so I tossed it, and today I'm just going to explain identities and graph identities so you have an idea of what they mean. I'm going to start with looking at identities that we already know. So identity is a word that we looked at a long time ago. You probably first saw it in middle school, where you defined it as the additive identity and the multiplicative identity. So we're looking at 7.1, which is all about identities and their uses. I'm going to define identity in a second, but I want to go back in time to where we first saw the word identity. And the first time that we used it was when we said, okay, you know that if we add 0 to anything, say we have 4 plus 0, we get 4. If we say x plus 0, we get x. So 0 is the additive identity. The multiplicative, you would say 4 times 1 equals 4, or x times 1 equals x. And so, I'm writing additive again. And so what identity means is it makes an equivalent statement. So they are equivalencies. That did not go as planned. It's completely gone now. Okay, there, pretty. So multiplicative identity is going to be 1. Multiplicative. All right. So these are things that you already know, but now we need to learn them for trig functions. So I've got over here on the side, I finally found it. Trig identities are equalities that involve trigonometric functions and are true for every value of the occurring variables where both sides of the equality are defined. So in this case, both sides are defined. This side has plus 0, but it's equivalent to 4. And I'm going to show you with graphs. I think that's the easiest way to see that things are equal when you graph them. And so I want to start with graphing these identities so you can see what I mean. So if you graph two equations, if you show where two equations are equal, you're going to show where they intersect. That would be show where they intersect. So for example, if I wanted to know where sine and cosine are equal, I can graph them. And I'm going to go through several graphs for you today. So let me find my graph. Here's graphing. Okay, let's say, for example, I just want to see where sine of x is equal to cosine of x. So these are equal at this point. Pi over 4, we know that has the same square root of 2 over 2, square root of 2 over 2. So sine and cosine are equal there. These are going to be a whole bunch of pi over 4 values, 3 pi over 4. So these are all the places that they're equal. Well, what happens if I go back to my identities that are right here? What if I'm trying to say, I don't want to see where the equations are equal at points. I want to see where, if I graph 4 plus 0 equals 4, what if I call this y1 and this y2? I want to see where those are the same. So if I graph 4 plus 0, there we go. And then for my second equation, my y2, if you will, over here, my y2, if I graph y equals 4, then they're the same line. They are equal everywhere. So I'm going to go back to my definition. Here it is. The identities are things that are true for every value of the occurring variables, meaning that y1 and y2 are equal everywhere. They're the same line. So identities are equal everywhere. And you already know that for adding 0 or multiplying by 1. You already know that. But I want to show you that with some trig functions. I have talked several times about how cosine and sine are the same graph, but they are shifted in one direction or the other. So we're going to change the trig now. I'm going to say y equals sine of x, and then I'm going to graph y equals cosine of x. Now they don't look like the same graph. They do not mirror each other. But what happens if I use an identity? And so I'm going to show you up here the different identities that I want to go through. Here they are. They're on your book on page 553. These are different identities that we're going to graph and prove. So the first one I want to show you is that sine of x right here is equal to a shift. This is a phase shift. This is equal to pi divided by 2 minus x. Did you see it happen? If I just graph the blue one, that's sine, and now if I graph this shift, cosine ends up being the exact same graph. So this is an identity. Sine of x is equal to cosine shifted. And I can do that for all of these. Earlier, I told you that cosecant was equal to the reciprocal. And we had that in what you did for me on Wednesday, where you had to explain to me further what a reciprocal means. It means that you're flipping it over. It doesn't mean that it's the inverse function. It means that it's the reciprocal, simply a fraction flipped over. So let's now graph those and see what happens. So if we graph cosecant of x, we get those up u's and down u's. What happens if I ask Desmos to graph 1 over sine of x? In black, it has now graphed the same function. They are the same. So what I'm trying to do with graphing them is give you a visual where you just don't believe me. You just don't push the I believe button that cosecant and sine of x are the same, that they're equal, but you can see it happen. We talked about how sine is opposite over hypotenuse, and so cosecant is hypotenuse over opposite. And these 6 identities, these are equivalencies, are things that you'll need to use in order to simplify our algebraic trig functions that we're going to do today. In most of what I wrote down for you, I wrote down tangent as sine over cosine or y over x. That may be one way that I would write that in my work. But here's your trig, your quotient identities. These are things that you probably already know, at least I hope so. But today we're going to show them as identities. So let's graph tangent of x on the left and see what it looks like. And let's ask Desmos to graph a quotient sine of x divided by, there we go, cosine of x. And it's not as exciting as watching on the calculator because it does it a little bit at a time, but does most graphs it quickly. But these are the exact same graph. So this is an identity. Okay, so on page 553, these should be things that you already know, at least the reciprocal identities and the quotient identities. Tangent is sine over cosine, and cotangent is the reverse. It's the reciprocal, so cosine over sine. Cofunction identities, I've talked about it briefly, but you may not have this memorized yet. You will need to start memorizing cofunction identities so that you can recognize these. Please note, and this is very important, that when it says, when it says sine of pi over 2 minus x, this is a composition of functions. This outside function is the sine function. That tells us that it'll be a repeating wave, and this tells us how the wave will be shaped. So it is the outside function, which is the main function, is sine. So it'll be some sort of wave. And then the inside function, pi over 2 minus x, it helps define the shape. But the point of me making this note is that this is not distributive property. It is not equal to sine of pi over 2 minus sine of x. You cannot do that. It is one function inside of the other function, and it is not distributive property. So this is very important for you to understand how not to do algebra on this. This is not distributive property. All right, so I've made that point. Let's look a little bit at some of our other identities. So I also have on page 554 another list of identities. And the first ones, these should feel pretty common for you. So let's look at them and they'll start to click and make sense. Let me graph them. Here we go. Okay, so if I get rid of these. All right, so sine of x plus 2 pi. Well, what does that mean? That means that sine of x has a period of 2 pi. That's not what I want. There we go. Here is sine. It goes to the origin. It has an up loop and a down loop, and then it starts to repeat. So from 0 to 2 pi, that's one period, and then it starts over again with the pattern. Well, what does that mean? It means that at 2 pi, it starts over again with the exact same pattern. So this period identity means that if I also graph sine of x plus 2 pi, then I've just started my graph right here at 2 pi. But it still goes backwards and it still goes forwards. It ends up being the same graph as this. In fact, x plus 4 pi would be the same thing. In fact, sine of x minus 4 pi would be the same thing. This is a period shift, but it just shifts it to the next period. It's like you're cutting fabric and you're looking at one pattern versus another pattern, or trying to put up wallpaper where the pattern repeats. So here I have period identities, meaning sine has a period of 2 pi. Cosecant is its reciprocal function, and it has a period of 2 pi. So if you add 2 pi, you still get the original function. Cosine, add 2 pi, you have the original function. Secant, add 2 pi, you get the original function. Tangent only has pi, because remember, it doesn't have an up loop and a down loop. When you look at tangent, It only has one shape. It's the same shape repeated over and over again. So it only has a period from this asymptote to this one of pi. If you add half pi to half pi, you get 1 pi, not 2 pi. So period identities, that's important. Even and odd identities. We have in my room, but y'all can't see it, some of the definitions that y'all did, and one of them was even and odd functions. And when we looked at even and odd functions, we looked at something like x cubed. And we said, well, what if you graphed negative x cubed? And I got a different graph there. Why did it do that? The whole thing is negative x. Oh, because it should give me the negative function. There we go. Now I fixed it. So when you plug in the negative value, you get the negative whole function value. Silly me. So we plug in negative x to see what happens. Let's do it with sine and cosine. I think it'll actually be easier. So sine of x. If you plug in a positive value, pi over 2, and then you plug in negative pi over 2, look at what you get. If you plug in positive pi over 2, you get positive 1. If you plug in negative pi over 2, you get negative 1. And this is a rule that we wrote down for odd and even functions. And odd functions say that f of negative x equals negative f of x. So in this case, if I plug in pi over 2 and get 1 as a point, here it is, pi over 2 gives me 1. What happens if I plug in negative pi over 2? Do I get negative y? And I do. So sine is an odd function. So every value that you get here on the positive side, you would get the opposite version on the negative side. The same thing happens with tangent. It is an odd function. It looks like x cubed, so of course it's going to be an odd function. X cubed is a 3, it's an odd function. The difference is cosine. Cosine, if you folded it, a piece of paper right here along the y-axis, you get exactly the same thing. So even functions, you plug in the opposite value and you get the same value out. So cosine of, let's do the same thing. Cosine of, let's do pi. Cosine of pi equals negative 1. That's a point. Pi negative 1. Cosine of negative pi, so cosine of plug in negative x, you still get negative 1. Negative pi, negative 1. So you have positive or negative input values and the same output. Here you have opposite output. So even or odd functions. And those are identities. They're shown here, eventually, on page 554, even and odd identities. Sine, you get the same, you get the opposite function, so it's odd. Cosecant is its reciprocal function, you get the same thing. So all of them are odd except for cosine and its reciprocal. So these two are even, the other four are odd. Then Pythagorean identities. We've talked about this a lot. I've already told you that sine squared plus cosine squared equals 1. That means the y value squared plus the x value squared equals 1. Well, there are other Pythagorean identities that come along with that. Tangent squared of x plus 1 equals secant squared, and 1 plus cotangent squared equals cosecant squared. And just to see what that graph looks like, That's just kind of interesting. And to put this in, you need to say cosine of x all squared. You can't really put in the squared in the inside, I don't think. Let's see, sine squared of x. Can you? You can. Oh, you can. Desmos will let you do it. Your calculator will not. Look how this is equal to 1. It is equal to a constant function 1. If you add tangent squared plus 1, you'll get secant squared. If you, so we could just look at that just to see. So tangent squared of x. So it's squared, see? It's not regular tangent that would go down and then down. And then we're going to say plus 1, and that's equal to secant of x all squared. And I just want to show you both ways that you can put it in your Desmos, for example. So here's blue and here's green, and they're the same function. So these are Pythagorean identities that come with that. Okay, so how do we use all these things? You're going to need to put into memory, and you might want to put a post-it note on these 2 pages so you can find them. We're going to use them to solve some equations. I'm going to go through some examples, and then you've got some practice today. Okay, our first example. Example 1. We're going to use identities to simplify expressions. My first example says cosine of theta plus sine of theta times tangent of theta. This is not a problem where I'm going to use a calculator and figure out how the graph goes, and I don't know how this graphs, and I don't want to graph it. It would be quite the XY chart. So instead, I want to simplify it. And to do that, I've written in red, rewrite all terms as sine or cosine. So I already have cosine of theta. I'm going to leave that. I have plus sine of theta. But tangent, I'm going to rewrite. So tangent, I'm going to rewrite as sine of theta over cosine of theta. So this part in red is tangent, rewritten as sine and cosine. So that's what we're going to do for almost all these problems. Then we'll find some sort of way to manipulate our problem so it simplifies. Okay, so what do we do here? Well, you're going to need to step into another world where you can consider sine and cosine to be an entire variable. In other words, when I multiply these 2 things together, this is going to be like a fraction times a fraction. I'm going to leave cosine theta, but I'm going to say sine of theta times another sine of theta is sine of theta all squared over cosine of theta. Now, for whatever reason, somebody decided that sine of theta all squared is equal to sine squared theta, with the squared being in the middle. These are equivalent, and I will usually write this one, but I just needed you to see what this is. But it's different. You cannot say sine of theta squared. That is equal to sine of theta squared. So you have to be very careful with your parentheses. All right, so be very careful with your parentheses so that you know you're writing this one. This one's the one that we're going to use most often. Okay, so how does that help me? Well, now I've got 2 fractions. So let's see, what did I do so far? Number 1, I rewrote as sine or cosine. Number 2, I multiplied fractions with fraction rules. They're not different rules, they're the same rules. Fraction rules, multiply top times top, bottom times bottom. And now I'm going to get a common denominator and add. Get lowest common denominator and add. So in order for me to have a denominator here, right now it's 1, I need to multiply by an identity. I need to multiply by 1. Funny how we started this lesson with that. So I need to multiply by 1. Well, I need to have cosine in the denominator. Therefore, I need to multiply by cosine of theta over cosine of theta. And as gross as that is, that's what we're going to be doing and practicing a lot. What does that give me? That gives me cosine times cosine in the top. That's cosine squared of theta. The book probably doesn't put parentheses around the theta, but this is the argument. This is the composition of functions that I was talking about earlier with making sure you didn't distribute. So the parentheses are actually very important. Anyway, I've got cosine squared on top. I've got cosine on the bottom. And I have plus sine squared theta over here over cosine of theta. I did not need to write that step out necessarily, but I wanted you to see it, especially in this first example. Now I have a common denominator. So I have a common denominator I can add. So here we go. Cosine squared theta plus sine squared theta over cosine of theta. Well, going back to my identities, if I move my stuff over a little bit, that's kind of gross. I don't think I'll do that. Let's do this. Here we go. Cosine squared theta plus sine squared theta. Look over here. Do you see anything that says cosine squared anywhere? Here it is. Cosine squared of x. It doesn't matter what the variable is. Sometimes your book will put a fancy b in there or an alpha, the Greek letters that are hanging in my room. So cosine squared plus sine squared, and order does not matter. This is equal to 1. Cosine squared theta. So this uses the Pythagorean identity right here, and now I have 1 over cosine. Is that the most simple? No. The most simple, the book wants you to say, what is 1 over cosine equal to? And it is equal to secant of theta. So what did we do? We said that this function that has 3 trig values in it is equivalent to secant of theta. And if you graph this and you graph this, they would be the exact same line. But this is the simplified version. So what did we do? We did trig algebra. We took something that was complicated and we simplified it. That we got secant of theta. Let's try another. Okay, so cotangent of alpha plus the fraction sine of alpha over 1 plus cosine of alpha. Some people will call this lowercase alpha. They'll call it a fish. I'm sure mine doesn't look like a fish, but they'll call it a fish. If you don't like the different letters that they use, you can totally rewrite this problem with just x. It is not a problem for you to change the variable into something that you like. But we're trying to simplify this. So I need to first put everything in sine and cosine. Cotangent, looking at your identity list on the other page. Okay, so now I've got them on the same page. Cotangent, if you need to look at your little cheat sheet, it is cosine alpha over sine. All right. Now, my alphas got kind of messy. I might actually change those to x's in a second. But here I have 2 fractions that I can't add together because they do not have a common denominator. So the least common denominator is going to need sine of alpha. This is one of the denominators, and that needs this one. 1 plus cosine of alpha. Which means that I need to give this one a 1 plus cosine, and I need to give this one a sine. And I do that by multiplying by 1. The 1 is going to have 1 plus cosine of alpha over 1 plus cosine of alpha. And this one needs sine. So now they have a common denominator. Sine and 1 plus cosine, sine and 1 plus cosine. So how does that help me? Well, now I have some multiplication to do. This is distributive property. Cosine is multiplied by everything in the top. So I'm going to have cosine of alpha plus cosine squared of alpha. Cosine times cosine is cosine squared. Plus sine squared of alpha all over my common denominator, which is 1 plus cosine of alpha times sine of alpha. Because when I multiply this by this and this by this, I get the same thing. And I'm going to leave that like this in the bottom in case it cancels later. Now I can add things together. I notice this will be used so often that I have cosine squared plus sine squared, and that's equal to 1. So this is equivalent to cosine of alpha plus 1, these two make 1, here it is, over 1 plus cosine of alpha times sine of alpha. So I suggest that you leave the denominator factored. That's really helpful because right here, if I put parentheses around the top and think about the order being switched, this one and this one are the same. So this factor and this factor cancels. I simplify to 1 over sine of alpha, and that is equal to cosecant of alpha. And I am simplified that one. So this is different, yet it has the same rules as everything you've done in algebra. So you're trying to get common denominators. You multiply two things together that are the same, and you get the same thing squared. You know that x squared plus y squared equals 1. So cosine squared plus sine squared equals 1. These identities, you might want to write them down on a piece of paper so that you can refer to them. You will need them to simplify the problem so that you can get to something very simple at the end. For homework tonight, you have a few problems to try so that you can try these on your own. Step 1. Rewrite all terms as sine or cosine. Then if you have something that says, okay, add, in order to add, you have to have a common denominator. That's 5th grade news. So you get a common denominator. Then you see if there are any trig identities over here that you can swap out. It's kind of like substitution. You swap out something that's equivalent. Identities are equivalencies. And then once you've swapped things out, you can simplify and have a simplified answer. So give those problems a shot. There will be a video that has solutions on Friday, but you need to post your problems Thursday for Thursday work. You can go over them on Friday, and we'll have some more to do on Friday in the same section so that you can get some good practice with identities. Okay, thank you very much. Have a great day.